You know, we've all been there. You pull up to the gas station and you see the two different handles. We all know you can't put diesel in a gasoline car or the other way around. But why? What's actually happening deep inside those engines that makes them so fundamentally different? Well, today, we're going to get under the hood and find out what's really going on. And trust me, the answer is way more fascinating than you might think.
And to really get to the bottom of this, we're going straight to the master text on the subject. It's a book called Internal Combustion Engine Fundamentals, written by MIT's own Professor John B. Haywood. I mean, this book is basically the Bible for engine engineers all over the world.
In fact, Professor Haywood's work is so comprehensive, so deep across all parts of automotive engineering, that he earned a nickname, the Yoda of Cars. So, with the Yoda of Cars as our guide, let's dive into the core principles from his work.
Okay, before we get into the big differences, let's do a super quick roll call of the key players you'll find inside almost any engine. First up, you've got the piston. That's what gets pushed down by the force of the burning gas. It's hooked up to the connecting rod, which then links it to the crankshaft. Now, the crankshaft is the star of the show. It's what turns all that up and down motion into the spinning power that actually moves your car. And of course, you have valves, which are like the gatekeepers letting air and fuel in and exhaust out.
So, at its heart, the idea is pretty simple. And hey, don't worry about all the formulas and arrows on this diagram. The main thing to get is this. Pressure pushes the piston, the rod moves that force, and the crankshaft spins. This basic mechanical dance is exactly the same in both engines. The critical difference, the one that changes literally everything else, is how they create that pressure in the first place.
And that right there brings us to the central distinction between these two engine types. Really, it all boils down to one thing: a spark versus a squeeze.
So, how do you get that fuel to burn and create the pressure that moves the piston? Well, it turns out gasoline and diesel engines have completely opposite answers to that question.
Okay, so a gasoline engine, what engineers call a spark ignition engine, it works like this. It mixes the air and fuel together first, sucks that mixture into the cylinder, compresses it a bit, and then uses a spark plug to set it all off. Just think of it like striking a match. A diesel engine, though, is a compression ignition engine. It does something totally different. It starts by taking in only air. Then it squeezes that air so hard that it gets incredibly hot. You know how a bicycle pump gets hot when you use it. Same idea, but way more extreme. And it's only then, into that superheated air, that it injects the fuel, which instantly bursts into flame. No spark plug necessary.
And this one single difference, spark versus squeeze, it has this massive ripple effect on how the rest of the engine works, right down to what happens when you press the accelerator pedal. So when you step on the gas, what are you actually controlling? Because as it turns out, it is completely different for these two types of engines.
In a gasoline car, when you push the pedal, you're opening up a valve called a throttle. This lets more of that pre-made air and fuel mixture into the engine. More mixture means a bigger bang, which means more power. Simple enough. But a diesel engine, it doesn't even have a throttle. It's always gulping in the maximum amount of air it possibly can. To go faster, you just inject more fuel into that hot compressed air. It's a much more direct way to control the power.
So it makes sense, right? Since the ignition systems are polar opposites, the fuels they use have to be opposites too. They are literally chemically designed for completely different jobs.
This part is so cool. Gasoline is actually engineered to resist igniting on its own. You only want it to burn when that spark plug tells it to. If it ignites too early just from pressure, that's what we call engine knock, and it's really bad for the engine. Now, diesel fuel is the exact opposite. Its entire job is to ignite spontaneously and reliably from just heat and pressure. So the very quality that makes a good gasoline is precisely what would make a terrible diesel fuel, and vice versa.
Okay, so we've talked about all these differences in theory. It's all been a bit abstract, but can we actually see them in action? Let's take a look at the data.
And the answer is a big yes. We can actually visualize this whole thing by looking at a graph of the pressure inside the cylinder as the engine is running. It's almost like seeing the engine's unique fingerprint.
All right, let's break this down real quick. The line going across the bottom represents time as the engine cycles through, and the line going up is the pressure inside the cylinder. Now just look at the two curves. That lower, smoother curve, that's the gasoline engine. You can see the pressure builds up more gradually as the flame spreads out from the spark plug. But the diesel curve, whoa, look at that thing. It's a much sharper, higher, and honestly more violent pressure spike. And that right there is the signature of compression ignition, a super rapid, really powerful burst of energy. So let's put it all together. Gasoline uses a spark plug, controls power with a throttle, and needs fuel that fights against igniting on its own. Diesel uses pure compression.
controls power just by adding more fuel, and needs a fuel that it ignites super easily. And because of that huge pressure spike we just saw in the graph, diesel engines have to be built much heavier and tougher to handle all those forces. And that is exactly why you see them in big trucks that need to be powerful and last forever. Understanding these fundamental differences isn't just a history lesson, it's actually crucial, because these principles are at the very heart of the challenges and choices facing the entire auto industry today. As our source material points out, those really high pressures and temperatures are what make diesel engines so fuel efficient. But, and it's a big but, that same exact process creates real challenges in controlling certain emissions, like nitrogen oxides and soot, which means they need really complex and expensive exhaust systems.
And all of this leads us to our final thought for today. For more than 100 years, these two competing designs have powered our world. But now, with the rise of gasoline-electric hybrids and fully electric vehicles, you have to ask the question, which one of these incredible, time-tested engines will be the first to become a museum piece? Well, the answer to that is still being written on the road ahead.